In this video, we are going to add our low temperature separator. This separator is not different from this one. It's a two-phase separator, but the difference it will be operating at lower temperature. Okay, so my inlet stream, which is gas to low temperature separator, the outlet, this is our inlet. We have two outlets, which is the vapor and the liquid. So this one will be LTS vapor, and the liquid outlet will be LTS liquid. So the connections, which is the inlet and the outlet, is enough for the separator to be solved. But in this case, because my main stream, which is inlet stream, is not defined, my LTS separator will not be solved. Okay, so we have added the connection and it's still not working. Okay, because some information is not defined. So now I have information about the gas to LTS. Okay, so now I'm given that the gas to LTS temperature is negative 20 degrees Celsius. Okay, so if I add this information, okay, it will be calculating and then it is converged. So when this one LTS vapor, we have, it's already returned back over here, and this is the stream coming back. When I define this one, I also define the temperature here and the temperature here. When I define the temperature here, the heat exchanger shell side will be defined. That's why my case now is solved. Okay, so now after adding the temperature, you will find out that your case is totally solved. Okay, so one specification was more than enough to add or to solve this case. To summarize, this one is an inlet separator at 15 degrees Celsius. Here we have a heat exchanger with a delta T, the temperature lower, about 20 degrees Celsius in this case. And after that, if we get closer, you know what is the delta T. The delta T here is negative 30 when we have lower temperature by 13 degrees Celsius. This one has a low temperature, and after that it is feeding a low temperature separator. So here we need to name this one LTS or low temperature separator. And if we check the parameter over here, it's a separator, a two-phase separator, and you can add a delta B if you have information, the vapor outlet delta B or pressure. This is your volume of this one. It's really important if we are dealing with a dynamic simulation. It's really important to know how to simulate or to calculate or to size your separator. And we have the percent of the liquid over here. Okay, so from the worksheet we have all the information printed. If we check the properties over here, this is the information printed. This is the composition of each stream, and this one is related to the dynamic, which is the pressure flow specification. Okay, so make sure to save your case now. And now we are going to talk about the balance operation. So what is the balance operation? This is a logical operation. Okay, which means when you are moving in your plant or your company, you will not find a balance operation, a physical unit. Okay, it's added to the simulation to adjust or not adjust, like to make sure that you are having a similar simulation to your actual plant. Okay, so the balance operation here, it's have a general purpose, which is a heat and the material balance. That's why it's called balance. There are several different balance operations. So here, if I look for the balance over here, this one is the balance. I'm going to add it here, and I'm going to talk to you more why I'm adding it. So if I double click to open this balance, we do have different balance. Like I can balance the component mole flow, or the mass flow, or the heat flow, or mole and heat flow, or mass and heat flow, which means I can balance is like equaling the molar flow between two streams. I want this mass stream. If we are talking about the mass flow, the overall balance is performed where the mass flow is conserved. Like the outlet stream will contain no composition, vapor fraction, temperature, or pressure. Okay, so we are dealing with the flow only. If we are talking about the heat flow, the overall balance is performed for only the heat flow is conserved. If we are taking the component mole flow balance, we are talking about the conservation of the component's mole flow. Okay, so I have added the balance over here, and in this case I am going to balance my inlet stream, which is my sales gas. What do I want to balance at this point? I want the dew point to be balanced, okay, by the component molar flow. Okay, let's keep moving and it will make sense after finishing it, because it's really difficult to understand what we are doing before adding the connection. So the outlet stream here will be hydrocarbon. I'm going to add it, which is hydrocarbon dew point. Okay, so the balance between the sales gas and this hydrocarbon dew point, and this type that we are talking about for this balance. So if we go to the parameters, we have different balance types, and this one is a component mole flow. So if we check this one, the component mole flow means the overall balance is performed here, which is the only molar flow of each component is conserved. Like combined outlet stream will have the same component flow rate as the inlet streams. Okay, so now after adding the balance and we choose the component molar flow, now we need to return over here, and this stream is not defined. Okay, so we are good to open this one, and usually when we open a new stream we are asked about the composition at the beginning, but for this one we are not asked because we already have done the balance. So the balance here, we took the molar flow and the molar composition of the sales gas and we give it to our dew point, hydrocarbon dew point. And here I am going to define the conditions. I want to specify the pressure to be 6000 kilopascal, and I want the temperature to be equal to, we are not giving the temperature, we want to make sure that our composition will be 100% vapor. Okay, so here what we have done, I want my sales gas, this one, my sales gas, which I am going to sell, will be at temperature at a pressure 6000, and it must be the vapor. So it has done the balance and find out the temperature will be negative 19.8. Okay, so here we are going to, if I am asking you about the dew point here we are 100% vapor. The dew point is the temperature where we are going to have our first drop of liquid. Okay, so again what we have done here, we have our sales gas, and this sales gas has a spec, which is I want to sell this gas. Okay, so if I can add this one in notes. Okay, I want to, in your plan, to have a specification of the sales gas to be, I want this gas to be sold at 6000 kilopascal and all vapor. Okay, so all vapor, which means the vapor fraction will equal to 1. How to add this spec? I want to balance this sales gas to know the temperature of the operation. So I am balancing this one, the composition and the molar flow, with another stream, and I'm going to define these conditions, which is the pressure and the vapor fraction for this material stream. It will balance between them and define over here your dew point. So this is the dew point. So this is the temperature at which you will start to have liquid. So we need to operate above this one. Okay, or if you are selling your gas at the dew point, this is the temperature of the operation.